Okay, so let's talk about Bohr models. Okay, Bohr models are named after an old white guy, a scientist, a chemist, Niels Bohr. And Niels Bohr kind of presented this idea that hey, maybe we can show how atoms are organized based on these like simple systems. And he was wrong, but that's okay. What's important and the reason why we use the Bohr model still is because it's a very simple way of showing information that we can use. And it really is very useful when you're learning chemistry to kind of see how atoms are organized, even if it's not technically correct, because what is correct is actually very, very complicated. So let me show you what a Bohr model looks like, right? So a Bohr model would be like saying, okay, in here, there are protons and there are neutrons, and this is the nucleus. Then around the outside, there are these energy levels. And these energy levels are where the electrons live. Sorry about that one. That one wasn't a very good circle, was it? Yeah, there we go. Still not that good, but better. Okay. So there would be electrons kind of like dashed in here, and they'd be like following these orbits, kind of like planets orbiting the sun. Okay. Now that's where this is wrong because this isn't what is happening. What is happening is that these electrons are somewhere around the outside of the atom and they're moving randomly in random directions and changing directions all the time. And the odds of an electron being in a specific place can be statistically um, formulated, but it's really hard to know for sure where an atom or where an electron ever is around the outside of an atom. So instead of doing these energy layers like this, a modern um, a modern model of an atom would show these clouds, which are kind of going to be these like statistical ideas that an electron's probably in this space somewhere inside of this area. And it could be here or it could be there, it could be there, but we don't know for sure. The odds of it being here are going to be shaded more heavily if we think that it's higher there and then lower, it's going to be, not shaded as much like an ombre pattern, right? So it starts very dark and it gets lighter as you go out away from the nucleus. And that's all very complicated. And you're probably like, what the heck's he talking about? Don't worry about it. All we need to care about is this thing right here, the Bohr model, right? So we've got these three different energy levels and there's more of them. So like the idea is that, you could have more energy shells. The bigger the atom is, the more of these shells it theoretically has and the more electrons it can hold and it can house. So let's just get rid of all of that because that's how you do a Bohr model. Now, I want to show you how to set this up and give you some cheat codes, right? Because it's actually very simple. And once you understand the concept of where these things come from, it's very easy to see, holy crap, the periodic table is organized for a specific way or in a specific way for specific reasons. One of those reasons is to help you do exactly what we're about to do with electrons. Okay. And another thing is, wow, like this really helps me to kind of understand how these atoms can interact with one another. And that's what we're going to do next. Okay, but first, let's talk about this thing, isotope notation over here, and how it doesn't look the same as what's going on here on the periodic table. Because look, if this is if this is our isotope and X is representative of any atom, so let's use hydrogen. Hydrogen's here. The atomic mass is what goes on top. The atomic number is what goes on the bottom, right? So if you go and look at your hydrogen on the periodic table here, our P table hydrogen has one on top, one's the atomic number, and then 1.008 is the atomic mass. Atomic mass is always bigger than the atomic number, and it's almost never a whole number. Okay. So that's a cheat code for you, right? So atomic mass is always the bigger one. It's almost never a whole number. If it's not a whole number, you round it to the nearest whole number. So this one we round down to one. Okay. So let's just fill this out for hydrogen. Okay. So the mass number up here is one. The atomic number down here is one. And the charge is actually that it's neutral. So there is no charge, right? So nothing goes here. Hooray. Okay. So what does that mean, right? The atomic number tells us the number of protons. Just reminding you because a lot of people had questions about that. So down here, that means there's one proton on this hydrogen atom, right? Okay. Now, we also know that the atomic mass is the protons plus the neutrons, right? So if our atomic number is one, that means there's one proton. If the atomic mass is one, that means there's zero neutrons, right? Because one plus zero is one. So zero neutrons. Now, we also know that when there's a charge, that tells us a story about whether or not it's going to be neutral or it's going to have extra neutron or extra protons or electrons. In this case, it's neutral, which means if it has one proton, it needs to have one electron, right? Because remember, electrons are negative and protons are positive. Okay. So we know that this is what a hydrogen atom has in it. Now, let's make the Bohr model, shall we? P equals 1, n equals 0, and then we throw one energy shell around the outside, and there's exactly one electron somewhere along that. That's it. That's the whole model. That's the model, the Bohr model for hydrogen. Okay. Hydrogen has one proton, zero neutrons, one electron. Boom, done. That's it. Simple as that. Now, remember in isotope situations, right? Isotopes have the same number of protons, but different number of neutrons, right? So bear with me for 1 second here. What if we were looking at hydrogen 2, aka deuterium? Deuterium would have one extra neutron. So what would change? Literally just that. That's it. That's how you would change it. Okay, let's make it tritium, shall we? Just for the lols. There'd be two neutrons, right? Because now our mass is three, two plus one, right? Remember, we want to keep it. I made a goof. We want to keep it neutral if we can, but we are just going to change the mass, right? That's it. That's how it changes. So does this really affect the Bohr model at all? No, it doesn't really affect the Bohr model at all. So every isotope of these things are going to have the same Bohr model, okay? But there's something called an ion that will change what the model looks like, and we'll talk about that in a different video. Let's keep it simple today, okay? So, how did I know to put one electron on this first shell? Great question. We know that this has one electron, right? And it has to go in that first shell. Now, let's talk about helium next, shall we? Okay, here we go. I'm just going to delete this actually, and then we'll talk about helium. Ready? Boom, boom. Okay, let's talk about helium. So helium, and let's go look at the periodic table together because I think this is something that people are missing. I want to help you with this. Let's click on helium. Helium is 2, that's its atomic number, 4.0026, that's its atomic mass or its mass number. So we know it has two protons and it must have two neutrons as well. So let's go and look at that. Okay. So our mass number is 4. Our Z, the atomic number, was 2. And again, everything that we do today is going to be neutral. So let's just not think about the charge. Okay, so we know we have two protons, right? And how do you get 4? 2 plus 2, right? So we must have two neutrons. And we know we need to balance the charges, so we must have two electrons. 2, 2, and 2. Very nice and fancy and easy, right? Okay, good. Equals 2. Equals 2. Mass equals 4. And we throw an energy shell around the outside, and we're going to throw two electrons in it, and we're done. Oops. 2e minus 1, 2. Boom. That's it. Easy peasy. That is the Bohr model for helium. Now, here's the thing, right? As soon as you are done with this first row, you jump down to the second row, and the second row has more than two elements in it, doesn't it? It actually has 1, 2, 3, 4, 5, 6, 7, 8. I'm going to tell you why that matters in just a second. All right, here we go. So I don't know if I just told you this or not. I've edited this video like 20 times. So if I said groups, that was not correct. Sorry. The rows are called periods. The columns are called groups. So in the first period of the periodic table, there are two elements, right? Now, that is actually going to tell you how many electrons you can put in your outermost energy shell, right? So for both hydrogen and helium, they only have one shell and it can have a maximum of two electrons. So for our helium atom here, its outer shell is completely full. Now, that's an interesting concept because if we look at the periodic table here, helium is in this very last row, isn't it? Let's use green. Let's use green. Helium's in this very last column, rather, this very last column, this last group, right? Now, everything in this last group is going to have a full outer. Is outer double T? I'm gonna leave it. If I made a typo, just it's fine. Sorry. Full outer shell. Okay. Which means that they're gonna have the full number of electrons in their outermost shell, which means that they are happy. These things here are called the noble gases, right? And they are stable and they are not reactive, generally speaking. Non reactive. Like they don't want to hang out with anybody. They're noble. They're chilling alone. Okay. They don't want to be friends with you. They don't want to be friends with anybody. They're fine. They have all the electrons that they need. They're happy. Okay. Now that's going to be important when we get into bonding later. Okay. And I'm going to keep talking about this happiness thing with these electrons and these energy shells as we go through this video. Okay. So those are the noble gases. So they have all the electrons they need. Now let's look at row 2. Okay. Row number 2 has got 1, 2, 3, 4, 5, 6, 7, 8. It's got 8, right? So let's use a number here. This has got 2. This has got 8. So the outermost shell in the first period can have 2 electrons. The outermost shell in the second period can have 8 electrons. And the same thing is true for the third period. You can have 8 electrons here. Now, things get weird when you get to row 4, when you get to period 4, because there are 10 additional elements, which means that this row can hold 18 electrons in their outer shell. Okay. Now, this is where the Bohr model gets a little weird. So, we're going to only worry about things in the first three groups, or sorry, the first three periods. I'm so sorry. even when I was in school, we had to know which name went to like each part of the periodic table, and we had to know the difference between periods and groups. And I would always get it wrong. I got like a 95% in chemistry because I couldn't remember the difference between period and group. I'm so sorry. Rows are periods. Columns are groups, or also called families back in the day, which is why it was confusing because I had two names for me. Anyway, doesn't matter. You don't care. Groups, wrong. See how I wrote groups right here? That was incorrect. It's actually periods, right? Okay. These things, the rows are called periods. Okay. All right, cool. Let's move on. So we have made a model of helium, right? Let's say we wanted to pull something out of the second row. Let's do carbon. Everyone loves carbon, right? So carbon has an atomic number of 6 and atomic mass of 12, right? So let's do carbon. Okay? Let's do the carbon model, and then I'll show you kind of why this is important and what we're doing with these electrons. Okay? So let's build it like this. We've got carbon. Carbon has an atomic mass of rounded to 12, and it has an atomic number of 6, which means it has 6 protons. So there's 6 protons. Oh man, this one's going to work out great for us. That also means there are 6 neutrons, right? Because the atomic mass is the neutrons and the protons combined, right? 6 of these, 6 of those equals 12. And we know that it's neutral, so it's going to also have 6 electrons. Okay, great. So let's go ahead and throw a nucleus together, and we know that P equals 6. And we know that N equals 6, right? Now, you guys all know that there's 6 electrons, but here's the trick. The first shell can only hold 2 electrons. The second shell can hold 8 electrons. Okay, so let's take our first 2 electrons. 1, 2. That's really great, right? And then we've got how many more electrons to put around the outside of this thing? We've got 4, right? And how we do it is we distribute it like on a compass, where we've got like north, south, east, west, right? So we're going to put 1 electron, 2 electron, 3 electrons, 4 electrons, right? Okay. Now you could have just gone like, oh yeah, like electron, 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 electron. Great, done. Technically, that's true, right? That technically gets the job done. Now, the problem with that is that when we get into what we're going to do next, it really is going to screw with your brain when we're talking about bonding. So, in order to make this work, let's go ahead and just put the electrons on like the 4 sides 1, 2, 3, 4. Now, if we had only had 6 electrons total and we couldn't add these last two, we would just write it like this, right? Or if we could only have 3 of the electrons, right? We write like this, and there's 4, right? Now we know this shell can hold 8, right? So let's say that instead of having 6, instead there's 10 electrons, right? That means we have to add 4 more electrons to this. Now that would make this not carbon. That would make this some bonkers crazy thing. So we're not gonna worry about what it's called. But just for the sake of showing you, you would then distribute the electrons again like this in pairs. Okay. That way the electrons are paired up because they like to be paired up. Shout out to all the pair. Okay. So this would be a full outer shell. Okay. So with this shell, we would be totally happy and our carbon would resemble very closely neon, right? Because it would have 10 electrons. The only thing that would make this different from neon is that its nucleus isn't the same, right? So this would be some crazy form of carbon that is what, 4 minus, right? That would be some crazy ion of carbon that would be 4 minus, right? 4 extra electrons, right? Um, we're going to discuss whether or not that's possible later. So why did I do that? I did that to show you. I did that to show you something. But let's go back to where we need to be, which is here. Okay, this is the completed diagram for carbon. Check, we did it. Okay, so that's kind of how you're going to do it, and you can actually kind of look at the periodic table to figure things out. So if we look at the periodic table here, hello periodic table, where'd she go? Hello, there it is. Okay. If we look at our periodic table, you can actually kind of see where things are going to be, right? So in the first period, you can have 2 electrons in the outer shell. You've got 1 electron in the shell, you've got 2 electrons in the shell. And then reading from left to right, it's very easy to count. In the second period, you can have 8 electrons in your outer shell. So this lithium is going to have 3 total electrons, right? Because it's got 3 protons, it's going to have 3 electrons. Those 3 electrons are going to be 2 in the inner shell, 1 in the outer shell, right? Beryllium, 2 in the inner shell, 2 in the outer shell. Boron, 2 in the inner shell, 3 in the outer shell. Carbon, 2 in the inner shell, 4 in the outer shell, like we showed you, right? 2 in the inner shell, 5 in the outer shell, 2 and 6, 2 and 7, 2 and 8, and it's happy, right? It's happy because it has a full outer shell. Full outer shells mean that it can't share or give or take electrons from things, right? It's not going to share its electrons anywhere. It's not going to give electrons to somebody. It's not going to take electrons from anybody. Fluorine, on the other hand, needs one electron to be happy, right? Because it's one electron short of having a full shell. Oxygen, two electrons short of having a full shell. Nitrogen, three electrons short of having a full shell. So they're happy to accept electrons and they will take electrons. So that's what's going to cause them to bond a lot of the time. And that's literally for later. Let's not worry about it right now. Okay. So using this same technique, right? If we know that neon would be, if we know that neon would be 10 and 20. Okay. So it would be 20 up here. It would be 10 down here, right? We know you'd have 10 of these. You have 10 of these. You'd have 10 of these, right? You know that to be true? So all we need to do to make the neon nucleus or the neon atom, the Bohr model, is we need to just add what we need to add to it, right? So we know that it has to have two energy shells. And we know that it's going to have 8 electrons in the outer layer to have a full shell and 2 electrons in the inner layer to have a full shell. Here's the trick, right? When you fill electrons, you have to fill from inside to outside first. So if we know something has 20 electrons, we put 2 in the inner layer and then 8 in the outer layer. That gets to 10, and then 8 in the next layer, right? So each energy level you can only put electrons in the next energy level once the current one is full. Okay. So let's just go and hypothetically look at something like magnesium, right? So magnesium has 12 protons, it has 12 neutrons, it has 12 electrons, right? So if you look right here, it even tells you where the electrons go, cheat codes. 2 on the inside, 8 on the next layer, and then 2 in the outer layer, right? So the inner shell full, the middle shell full. The outer shell has 2 electrons. Okay, why do I keep focusing on this outer shell? Those electrons are called valence electrons, and we're going to use them for things like bonding. Okay, so when you're looking at the work that I have you doing this week, you might see something that asks for the number of valence electrons. The number of valence electrons is how many electrons are in the outer shell. Okay, let me write that down for you. Okay, I'm going to use a different color because I'm nice. Valence electrons equal electrons in the outer, and I might have spelled that wrong again. I'm gonna have to look that up. Is outer with one T or two? Shell. Okay. So we are only gonna focus on regular elements. If you see something about ions on the homework or the work that you're gonna try to do, I don't want you to do it. Don't worry about ions right now. Okay. We're gonna worry about ions in the next video, and that's what we're gonna do tomorrow. Okay. So hopefully that helps you. And I know I told you a bunch of stuff about bonding. We haven't got there yet, but this is a preliminary kind of giving you to that point. Okay. Thanks for watching.